Thank you for joining me. Today we're going to dive into a new piece of polynomials. So we've talked about a lot about them already in just a couple lessons. We've talked about standard form, naming, end behavior, mins and maxes. Today we're going to move on to this idea of zeros of a polynomial. This is something you've kind of already seen with quadratics, but we're going to extend it to all polynomials now because that is the point of this chapter. So what is this saying? Well, it's saying that x minus a is a factor of the polynomial if and only if a is a zero of that related polynomial. Now when I say zero, there's a lot of different things we can mean. You can say zero, solution, root. You can even say x-intercept because graphically these zeros are where your function is going to cross the x-axis if you were to graph it. And I'll show you that in a little bit. So what does it mean? Well, what this means is, and again, you've seen this with quadratics, that if you factor a polynomial, then those factors you can use to find the solutions using the zero product property. So again, this really isn't anything shocking to you. This is what you've already seen. We're just going to take it a step further in Algebra 2. So for example here, find the zeros of each polynomial function. All right, well, again, the zeros will be what would make this equal to 0, what would make this equal to 0, and what would make that equal to 0. Okay, so each individual piece, we want to know what would make that equal to 0. Well, I think these are pretty easy. So here, obviously, -2 would make that first piece equal to 0. 1 would make the second piece equal to 0, and 3 would make the third piece equal to 0. Okay, so again, usually you guys can use shortcuts. You may not have to show that middle step. Again, for those of you that need to visually see, well, each of those factors need to equal 0. You could set it equal to 0 and then do the algebra from there. Same thing over here. So here, x, well, if there's ever something just sitting out front, if you set it equal to 0, well, obviously x just equals 0. That x plus 4, if we set that equal to 0, obviously if x were -4, that parenthesis would be 0. And then 2x minus 3, this is the one I actually do encourage kids to show me a little bit of work for, because this one takes a little bit more manipulation to get. You have to add the 3 and then divide by 2 to find where that one would be 0. All right, so again, what you've seen before, you literally just saw this when we were doing quadratics using the zero product property. But again, of course, in this chapter, we're going to take it a step further. That step further is now going to introduce this idea of multiplicity, of sometimes the same factor can be represented more than once in a polynomial, okay? So when you find that 0, what you're going to say is a is a 0 of multiplicity than whatever that exponent is, okay? So the multiplicity deals with the exponent that you see, okay? And again, let me show you what I mean by that. So here I'm going to take this first one, x minus 1. So obviously the 0 would occur when x equals 1. If I use 1, that thing is going to become 0, that parenthesis will. But notice that exponent of 2. That is this thing's multiplicity. That solution of 1 is appearing twice in that polynomial. So right beneath this, I'm going to put that it has a multiplicity of 2. The next one, that x plus 5. Well, obviously that creates a solution or creates a 0 when x is -5. If I plug in -5 to that parenthesis, whole thing becomes 0. Now here, notice there is no exponent attached to that one. So this is just kind of the normal case with multiplicity 1, right? is just appearing once in that polynomial, because anytime you see something, it secretly has an exponent of 1 if there's no exponent showing. Then this last one, that x plus 4 to be 0, well again, that's going to happen when x equals negative 4. And this time, notice that it's being represented 3 times in that expression because of that exponent. So we say that that 0 of negative 4 has a multiplicity of 3. We can do the same thing on this next one. So here we have x equaling 0. Okay, and again, whenever you just have an x or x with a number sitting out front, its 0 is actually always 0. Okay, now here, notice the square. Okay, so again, that exponent is your multiplicity. So that solution of 0 has a multiplicity of 2. It's represented twice because it's an x squared. That x plus 7, well, for that to be 0, we're looking at negative 7. If I plug negative 7 into that, that becomes 0, that expression does. And again, notice this is a case where there isn't an exponent showing, so that means it's just being represented once, okay? Multiplicity 1. And then just like I said up above, those a little bit more complicated ones like this is a time that maybe you can get by all the others without showing the algebra. In this one, I really do encourage you to. Show me setting that 2x minus 5 equal to 0, add the 5 over, divide by 2. So this one has a 0 at 5 halves, okay? It has a solution of 5 halves. And its multiplicity, well, that thing is being represented 5 times in this expression. So that's the basics of zeros and multiplicities, okay? If it's in factored form, you can very easily use zero product property on it. The multiplicity simply comes from the fact now that you can have exponents attached to these things, okay? So let's talk a little bit more about where this is going. So I talked about whenever you have a 0, that is where it crosses the x-axis. So I've actually graphed one of these things for you, okay? And notice this solution of x plus 1, notice that would be a solution of x equals negative 1. And notice that's exactly where it's plotted. Here, notice this would have a solution at 3, because that's what would make it 0. Notice that is where it's crossing the x-axis. Okay, so graphically, when you're finding these zeros, what's happening is that is where it's crossing or touching the x-axis. That's going to become very, very important later in this chapter. So if you can grasp that idea now, you're going to be so well off later in this chapter. Now, notice the difference in their behaviors, though. So the green one I just put, notice it has an exponent of 2. And notice how it's acting like a parabola. An exponent 2 acting like a parabola. It's actually not crossing. It's actually just touching it, turning around, giving that kind of parabolic shape. Any even multiplicity is going to do that. Okay? Then, for this one, an odd multiplicity will act like a line and just go through the 0, okay? So when we're talking about understanding general shapes of these polynomials, that is something very good to know, okay? So we talked about how to find it when it's in factored form. So obviously the next step would be, well, what if I just give you a polynomial? Well, again, this isn't too far of a stretch. You've seen this before. I can factor that, right? All I'd have to do if I give you something that looks like this, all you'd have to do is factor this and say, all right, x plus 10 and minus 2, because that multiplies to negative 20, adds to 8. To find my solution for that, well, Negative 10 would make that 0. What would make that 0? Well, if x were 2. So again, just like in chapter 4, you can factor these things and then find the zeros from there. Here, this would factor into a -7, -7. And now again, we can get really fancy and call that x minus 7 squared. So the solution, what would make that equal to 0? Well, the solution would be at 7. 7 would make that thing 0. But notice the exponent. So with multiplicity 2, that solution of 7 would be represented twice in that polynomial, in that quadratic expression. All right, so we spent a lot of time so far finding zeros, right? Starting when I give you the factored form, can you find them? Then if I just give you a polynomial, can you factor them and find them? Now we're going to go backwards. We're going to talk about the fact that if I know the zeros, I can write a polynomial that has those zeros as a solution, okay? So what I want you to notice is here, if I have a solution or a 0 of 4, that means that the factor that created that had to be x minus 4. If I have a solution of -5, that means a factor of x plus 5 is what created it. So really what's happening here is notice there's a sign change. Okay, there's a sign change from the 0 to the factor that created it. And that is going to be very, very important. Okay, because, for example, if I wanted to write a quadratic polynomial with zeros, 3 and -1, so I have the solutions already, I have the zeros, I want to reconstruct the polynomial that created that. Okay, if that's my goal, well, that solution of 3, that had to come from x minus 3, okay? Because if I put 3 in there, it makes that thing 0. If I have a solution of x minus 1, or sorry, of -1, and x plus 1 had to be the factor that created it, because if I plug -1 in, that becomes 0. All right, so you always get this sign change. When I give you a 0 and I ask you to reconstruct the polynomial, the factors always have a sign change. Now, also notice, I talked about wanting it in standard form, okay? That standard form, now I'm going to FOIL this thing out, okay? So, foiling this thing out, I get x squared plus 1x minus 3x minus 3. Clean it up a little bit by combining my like terms. 1x minus 3x is minus 2x. And there we go. There is our polynomial with zeros, 3 and -1. And we can keep this going too. So write a cubic polynomial standard form with zeros, -2, 2, and 3. So here, same thing, just a little bit longer. So to have a solution of -2, an x plus 2 would create that. Again, because if I plugged in the -2, that becomes 0. This 2 here, again, I need to flip the sign, because if I plug 2 into that, now that second parenthesis would be 0. Again, sign change. So if I plugged the 3 into that parenthesis, it would become 0. So here I have 3 parentheses. Now, I'm going to urge you to FOIL intelligently here, okay? What I mean by that is if you ever have two things that are the same but opposite, I would encourage you to FOIL those together first. All right? So I get x squared, 2x minus 2x. That middle part just cancels out right away, so I don't even have to worry about it. Then I get my negative 4, and then I still have that x minus 3 sitting up back. So now you've probably guessed I'm going to have to FOIL this again. So x squared times x to the first will give me x cubed minus 3x squared minus 4x plus 12. Here is my polynomial in standard form. So notice when you get higher than a quadratic, when you get to cubic, stuff like that, you will have to FOIL more than once to make this process work, okay, to finally get it to be in its standard form. Write a cubic polynomial in standard form with zeros 1, with multiplicity 2, and negative 3. Now when I say with multiplicity, okay, so 0 of 1 would mean this. With multiplicity 2 means there's going to be 2 of them, okay? So I have 2 of those. And then I have that. So again, always noting the sign change that's occurring. And now, same thing, I just have to go back and I have to FOIL this out. So to FOIL this out, I get x squared negative 1x minus another 1x would give me a negative 2x. Negative 1 times negative 1 is a positive 1. And now notice I still have to multiply again. So this is FOIL-like. And again, you saw this back in Expo, but obviously the acronym itself doesn't work in this case when you start getting bigger things like this. Okay, so what I end up doing here is I'll take this x and I'll multiply it to everything. All right, so that's going to become an x cubed minus 2x squared plus x. Then, same thing with the 3. Multiply the 3 to everything. That actually has the same effect as the FOILing process. If you just go term by term, multiply to everything in the other parenthesis, again, exactly same effect as you would have by FOILing, since technically you can't FOIL these bigger ones. And now I'm just going to combine up my like terms to make it look pretty. So my x cubed, well, there's no other x cubes. Negative x squared plus 3x squared, negative 2 plus 3 is a positive 1. 1x minus 6x is going to be a negative 5x, and then a plus 3. So a little bit more work for that one. But again, the process is exactly the same. Create your zeros, start FOILing and multiplying until you get to your standard form. So I wanted to take this opportunity to go backwards from that. Okay, so I want us, now that we have that polynomial, I want us to go and think about all the things we've talked about already. Okay, for example, naming it by degree. So its degree is 3, so I'm going to call this a cubic. How many terms does it have? Well, 1, 2, 3, 4. So remember, there's no special name for that, so we just say polynomial of 4 terms. End behavior. Well, This is an odd power, right? An odd exponent. So we're going to think of it like a line. And the fact that this is positive means we're going to think of it as a positively sloped line. Okay? And again, what that means is that its end behavior is starting down and ending upward. Okay? So that's probably the trickiest part is remembering that. Now, here's another little new thing, okay, that I just want to show you to introduce you to the idea that we can sketch these things now. So, we have our zeros, okay? We have a 0 at 1, actually 2 zeros at 1, and a 0 at -3. Okay, so we precisely know those points are on this graph. Remember, the solutions or the zeros are where it crosses the x-axis. And now we also know the end behavior, right? We know that this polynomial on the left-hand side is starting down. So our polynomial is starting here. Then we talked about when the solution has an odd power. So here, this has an odd power. So it just goes through it like this. Well, it's going to have to curve back down eventually. We don't know how high it goes, but it's going to have to curve back down to head towards this 0. Now remember that 0 is special because doesn't that 0 multiplicity of 2, remember even multiplicities is going to bounce off of the function. So it's going to bounce off of the x-axis here, turn back around, and that's how you can see that right-hand behavior of ending upward. Okay, so again, all these things that I'm showing you, they're really cool because it's setting the stage that you can actually draw rough sketches of this. Obviously, I don't know exactly how high or low this thing ends up going. However, that gives me a general shape this function is going to have. Now, let's talk about that general shape. Okay, so we also know how to find those relative max and mins. Okay, so I actually am going to go in my calculator and review that skill with you. So if you go to y equals, clear out anything that's there, I'm going to type in my function. So x cubed plus x squared minus 5x minus 3, I think it's a minus 3, plus 3. If we go to graph that, there we go. And yes, it looks just like what I just made. Now, we can use the calculator to find how high and low those arches go. Because remember, the calculator can find the relative maxes and mins for us. So, remember to do that, I'm going to go into the calc feature. I'm going to do the maximum first, okay? Because I want to know how high is that going. All right, so remember it's telling you left bound. So I'm going to go till I'm left of that point, hit enter. Now it's prompting me right bound. I'm going to go right of that point, hit enter. And there we go. So my max is occurring at the point -1.67, 9.48. Now let's find the min, because the min is going to be right there. Calculate. Minimum, same game. It wants me on the left of it. Well, all right, I'm on the left right now. To the right of that point. Now I'm to the right of it. Hit enter. So my min is going to be at 1, 0. which makes sense because we know it's sitting on the axis. So again, that should actually make sense to us that it's 1, 0, okay? Because we knew that it was sitting right on the x-axis where it's curving. So again, I hope you're starting to get the big picture of how all these things come together to give us our solutions and to see why we're doing all this. We can construct these polynomials. So do take a moment, and I would love for you to write me that summary. Summarize what it is that you're getting out of today, the big ideas you think you need, and then come back to class ready to do your practice work.